So now we would like to demonstrate that Hamilton's equations follow from the principle of least action. So we recall that the action is defined as the integral of L dt. And we had found that we needed to have a stationary point of the action, which then means that we have a stationary point for the variation of the integral, L dt. And so this has to be equal to 0 in order to have our least action. So if you recall, we defined the Hamiltonian via a Legendre transformation, Q alpha dot P alpha minus L. And now we're going to turn this around. So we define L to be Q alpha dot P alpha minus H. And just to emphasize, H is a function of Q alpha, P alpha, NT. And so now we will insert this expression for our Lagrangian into the equation for the stationary value. And as we have demonstrated previously, we can reverse the order of the variation or the integration. And so I can define then the variation in S as an integral and bring this variation inside of the integral. And so I have a sum over alpha of variation of Q alpha dot P alpha minus a variation of H. And this whole quantity then is integrated and has to be equal to 0. So now we evaluate each of these terms. And so I'll write that ds is an integral. I have a summation. And then I have P alpha delta Q alpha dot plus Q alpha dot the variation of P alpha, and then I subtract, and now I need the variation of H, so it's di H by di Q alpha delta Q alpha minus di H by di P alpha delta P alpha. And there is no term with respect to time, because recall that the variation explicitly means that dt is equal to, or delta t is equal to 0. And so these are the only terms that I have. So this is our equation for the variation of the action. And now I want to focus on this term in particular. So we are integrating P alpha delta Q alpha dot dt. And I'm going to do this by parts. And so I will set u to be P alpha. So du is P alpha dot dt. And then notice here that we have delta Q alpha dot, which is delta d by dt of Q alpha. And I can reverse, of course, the order of this operation. So this is d by dt of delta Q alpha. And so my other variable I will have dv will be this delta Q alpha dot, which I can write as d by dt of delta Q alpha dt. And so v then is just delta q alpha. And so when I perform this integration, this is equal to uv. So I have p alpha delta q alpha, and then minus the integral of v du. So that is a delta q alpha p alpha dot dt. So this integration is over an interval from ta to tb, and by definition, the delta q has to vanish. So when I put in these limits, that term has to vanish, because recall how delta q is defined. It's a variation in q, but it always has to satisfy the constraint that the variation vanishes at the boundaries. So remember, in our derivation of the calculus of variations, we always had that at the boundaries of the interval, the variation had to vanish. So this term vanishes, and so I can replace this integral of p alpha delta q alpha dot dt with minus delta q alpha p alpha dot dt. So when I make this substitution then, and it's easiest to do this directly here, then I substitute p alpha dot delta q alpha, and then there's a minus sign. So that now we have this expression for the variation. And if you recall, this variation must be set equal to 0 to have an extremum point. And so to have this vanish means that the terms that involve the variation in q have to cancel, and the terms that involve the variation in p have to cancel. And so we immediately have then that q alpha dot has to equal the partial of the Hamiltonian with respect to p alpha. So when I make that equivalence, that term will vanish, and that p alpha dot has to be minus the partial of the Hamiltonian with respect to q alpha. So from the principle of least action, we get back Hamilton's equations.